Outside your window, on a quiet night, the sky above your small blue world is calm. Streetlights glow, a few stars peek through, and somewhere behind the dark air and thin clouds, distant planets move slowly along their ancient roads around the sun. As you rest under your blanket, your heart beats steady and familiar. Light from those worlds is crossing space toward Earth. It travels for hours and hours, a gentle stream of photons, before it ever reaches a telescope on a mountain or a sensor in orbit. Most of the planets sending that quiet light are ones you know by name. Mercury and Venus close to the Sun, bright and quick. Mars rusty and compact. Then the great gas giants, Jupiter and Saturn, swollen with hydrogen, wrapped in bands and rings. Far beyond those familiar giants, almost forgotten in the hazy edges of the solar system, two colder worlds drift in their wide circles. Uranus and Neptune, the outer ice giants, are so distant that sunlight is more like a pale memory than a warm touch. These distant planets look, at first glance, like soft blue marbles. Through small telescopes they can seem simple, almost featureless. But inside each sphere, beneath their hazy clouds, lie deep layers of exotic matter and long, slow stories of formation and change. Tonight we are going to wander, gently and unhurried, into the story of these two worlds. As your body settles and your breathing softens, we will trace how they were discovered, what we know about them now, and why they matter for a world like yours. In a moment, we will step back in time to when Uranus was not yet known as a planet at all. But for now, you can simply notice the weight of your body on the mattress, the way gravity holds you as firmly to Earth as it holds distant moons to their giants. A good place to begin is with distance, because distance shapes everything out there. Earth orbits at about 1 astronomical unit from the Sun, a unit defined as our average distance, about 93 million miles, or roughly 150 million kilometers. Uranus circles the Sun about 19 times farther out than Earth does. Neptune travels even farther, about 30 times Earth's distance. At those ranges, the Sun is a bright star rather than a disk, and sunlight is weaker, stretched thin across enormous space. If you could ride a quiet spacecraft outward from Earth at the speed of a fast jet plane, it would take many years just to reach Uranus and many more to reach Neptune. The outer solar system is not crowded. It is wide, sparse, and patient. This great distance is one reason the outer ice giants were among the last major planets to be known. To early observers using only their eyes, Mercury, Venus, Mars, Jupiter, and Saturn were the visible wanderers, bright points that moved against the background stars. Uranus is just barely bright enough to see without a telescope under very dark skies, but it looks like any other star. For most of human history, it went unnoticed as a planet, blending into the familiar patterns people used for navigation and for stories. That changed in the late 1700s, when an astronomer named William Herschel swept the sky carefully from his garden in England. Using a telescope he had built himself, he noticed a small object whose disk looked slightly larger than a star. At first, Herschel thought he might have found a comet, because comets were known to drift slowly against the stars. But as he and others followed its motion over months and years, the path made more sense as a nearly circular orbit far beyond Saturn. Gradually, astronomers realized that this slow, pale, bluish object was not a comet at all, but a new planet. It was eventually named Uranus, after an ancient sky deity, extending the family of known planets outward and widening the map of the solar system. If you imagine the people of that time, working with glass lenses and hand-drawn charts, you can sense how surprising it was to add a whole new world to the list. The sky they thought they knew so well had quietly been hiding another member of the solar family. Discovery did not stop there. Once Uranus was tracked carefully, astronomers noticed something odd. Its orbit did not fit perfectly with the predictions made using Newton's laws and the gravity from the Sun and known planets. There were tiny but persistent discrepancies. Those small mismatches led to a gentle but profound question. Was there yet another planet, farther out, tugging slightly on Uranus and disturbing its path? If so, where should observers point their telescopes to catch this unseen world in the starry background? Two mathematicians, working independently in the 1840s, tried to answer that question. Urbain Le Verrier in France and John Couch-Adams in Britain both used the tiny irregularities in Uranus's motion to estimate the mass and position of a possible new planet. Le Verrier sent his prediction to the Berlin Observatory. On a clear September night in 1846, Johann Galle and his assistant looked where the calculations suggested. Within a narrow patch of sky, they found a small disk that moved, just as predicted. That moving point of light became Neptune, the eighth major planet, discovered not by accident but by mathematics. Its existence was inferred from its effect on another world before it was ever seen, a quiet example of how far reasoning can reach across space. While you lie here, feeling your own weight on Earth, it can be calming to think about how sensitive those old measurements had to be. Tiny deviations in one planet's orbit, barely noticeable, were enough to reveal another planet billions of kilometers away. Even after Uranus and Neptune were added to the charts, they remained elusive. Through the telescopes of the 19th and early 20th centuries, they appeared as small, bluish disks with few visible features. Details of their surfaces and atmospheres stayed hidden. At that time, astronomers grouped Jupiter, Saturn, Uranus, and Neptune together as gas giants, assuming they were all mostly made of hydrogen and helium. Only later did scientists realize that Uranus and Neptune belonged to a different category: the ice giants. In planetary science, the word ice does not mean frozen water alone. It refers to substances like water, ammonia, and methane that can be solid or liquid at the temperatures and pressures found in the outer solar system, very different from the familiar surface of Earth. Uranus and Neptune still have envelopes of hydrogen and helium gas, but a much larger fraction of their mass is in these heavier molecules. Their interiors are thought to be thick layers of water, ammonia, and methane in strange high-pressure forms, over dense rocky cores. We will explore those interiors more deeply later, but for now it is enough to know that they are not simply scaled-down versions of Jupiter. They represent a different outcome of planet formation, a different balance between light gases and heavier, volatile materials. As you listen, you might notice your own breath rising and falling with a slow rhythm. That same rhythm exists on grander scales in the solar system, where gas and dust once swirled, settled, and clumped into the seeds of planets, including the ice giants far from the sun. Long before Earth had oceans or life, the young sun was surrounded by a rotating disk of gas and dust. Close in, where it was warm, rock and metal grains could survive. Farther out, where it was colder, ices could condense and accumulate, adding more material to growing worlds. In this cooler zone, beyond the early orbits of Jupiter and Saturn, cores of rock and ice grew. Some became massive enough to gather thick blankets of hydrogen and helium, turning into gas giants. Others, like the precursors of Uranus and Neptune, captured less gas but more ice. The exact details of how and where Uranus and Neptune formed are still being studied. Some models suggest they formed closer to the Sun and later migrated outward. Others place their birth zones nearer their present orbits. The truth may blend several ideas together. Whatever their precise pathways, the result is two planets with similar sizes and masses, both about 4 times Earth's diameter and around 14 to 17 times its mass. To our instruments, they look like siblings, yet their behaviors and histories are not quite the same. Even with telescopes, for a long time we could only guess at their winds and weather. Subtle changes in brightness hinted at cloud bands, storms, and shifting hazes. But their great distances made every measurement hard-won, like listening for a whisper across a noisy room. Here on Earth, if you step outside on a clear winter night, you can feel the air against your skin and see clouds moving overhead. On Uranus and Neptune, similar processes of fluid motion are unfolding, but in atmospheres made of hydrogen, helium, and methane under dimmer light. The pale blue color of both planets comes mainly from methane gas in their upper atmospheres. Methane absorbs red light from the sun and allows blue and green light to scatter back toward space. The result is the soft, cool hue captured in so many images and illustrations. Yet even in this similarity there are differences. Neptune's blue is often deeper in photographs, and its atmosphere shows more obvious storms and bands. Uranus, especially in older images, appears more uniform and pale, like a calm sphere with few visible markings. One of the great puzzles about Uranus is its tilt. Unlike Earth, which leans only about 23 degrees from upright, Uranus is tilted by roughly 98 degrees. It is essentially on its side, rotating almost like a rolling ball rather than a spinning top. This extreme tilt means that each pole of Uranus experiences long seasons of sunlight and darkness. For many Earth years, one pole points almost toward the sun and the other points away. Then the situation slowly reverses. Day and night there follow a very different rhythm. Scientists think this tilt may be the result of a giant collision early in the planet's history, perhaps with a body as large as Earth. Such an impact, in the turbulent youth of the solar system, could have knocked Uranus over without disrupting its orbit around the Sun. Neptune, by contrast, has a tilt more like Earth's, around 28 degrees. But it is livelier in other ways. Measurements show that Neptune has strong winds, some of the fastest in the solar system, and a greater internal heat flow than Uranus. Despite being farther from the Sun, these contrasts raise quiet but persistent questions. Why does Uranus radiate so little internal heat compared with Neptune? How exactly did it end up so tilted? Why do two planets of similar mass and composition behave so differently? The answers are still not fully known. As you lie here, you might let those unanswered questions drift by like clouds. They are not urgent problems. They are gentle mysteries. Scientists collect each small clue, hoping to fit them into a picture of how planets evolve and why worlds can turn out so unlike one another. Before the age of spacecraft, our view of Uranus and Neptune came entirely from Earth-based telescopes and, later, instruments in near-Earth orbit. Each new generation of optics, detectors, and image processing sharpened the picture slightly, bringing faint patterns into focus. Still, much remained hidden behind distance and blur. There were hints of rings, traces of moons, and suggestions of complex atmospheres, but the details were uncertain. To truly know these ice giants, eventually something more than distant observation would be needed. It would take a robot traveler, launched from your own small blue world and coasting for years through deep space, to pass close enough to see their clouds, measure their fields, and feel their gravity directly. That part of the story belongs to a later chapter in our journey. For now, as this chapter of our quiet exploration comes to rest, you can simply hold the outline of these distant planets in your mind. Two cold, blue worlds, born in a disk of gas and dust, discovered through patient watching and careful calculation, still holding many secrets. When we paused before, you were resting on your small blue world while a single explorer aimed for the ice giants. That traveler was Voyager 2, launched by NASA in the year 1977, a quiet machine the size of a small car, carrying cameras, sensors, and a golden record. Voyager 2 did not rush straight to Uranus and Neptune. First it slipped past Jupiter, then Saturn, dipping into their gravity fields. Each flyby bent its path and lent its speed, like gentle pushes on a swinging door, guiding it outward along a carefully planned grand tour. By the time it neared Uranus in the month of January, 1986, Voyager 2 had been traveling for more than 8 years. People on Earth were driving to work, cooking dinner, tucking in children, while far beyond Saturn a metal visitor was quietly arriving at a pale blue world. As Uranus grew from a dot to a disk, Voyager 2 slowly turned its white dish antenna toward Earth and its sensitive instruments toward the planet. Radio commands left your world from giant antennas and, hours later, the spacecraft answered with a thin, steady stream of data. You can imagine those antennas in California, Spain, and Australia, tall ribs of metal standing under the night sky. While people nearby slept under blankets like yours, the dishes listened for whispers billions of kilometers away, catching signals weaker than a watch glow across a room. Voyager 2 skimmed about 81,000 kilometers above the cloud tops of Uranus, closer than the distance across Earth. In just a few hours around that closest approach, it changed our view of the planet, turning a fuzzy circle into a place with weather, rings, and many moons. The visible atmosphere looked surprisingly calm. Compared with the roiling bands of Jupiter, Uranus appeared smooth and muted, a soft aquasphere with only faint stripes and tiny storms. Sunlight and viewing angles hid many features, giving the planet an almost sleepy, featureless face. Yet beneath that calm appearance, instruments sensed motion. Winds in the upper atmosphere blew mostly from east to west at hundreds of meters each second. Temperature profiles showed layers of warmer and cooler air, revealing that Uranus was not frozen still, only quiet to human eyes. Then came one of the strangest findings, the magnetic field. On Earth, the magnetic field is roughly aligned with the spin of the planet and centered near the core. Voyager 2 found that Uranus's magnetic field was tilted by about 60 degrees and shifted far from the planet's center. This meant that as Uranus rotates, its magnetic bubble, the magnetosphere, does not simply spin like a neat top. It wobbles and twists, sweeping through the solar wind in complex patterns. Charged particles slide along field lines that keep changing direction with each slow turn. For scientists, this odd geometry was a quiet but powerful clue. A tilted, off-center field suggested that the electrically conducting layer generating the magnetism might lie in a shell of strange, hot water mixed with ammonia, rather than in a small metallic core like Earth's. Voyager 2 also confirmed that Uranus wears rings. From Earth, astronomers had seen stars flicker as these rings passed in front of them, but the pictures were blurred. Up close, the spacecraft counted 11 narrow rings, thin and dark, with hints of dusty bands threading between them. Those rings are made of small pieces of rock and ice, coated and darkened by radiation from the sun and charged particles. Their extreme narrowness suggests the presence of shepherd moons, little unseen companions whose gravity gathers and guides ring particles into tight, sharp lanes. Before the flyby, only 5 sizable moons were known around Uranus: Miranda, Ariel, Umbriel, Titania, and Oberon. Voyager 2 discovered 10 more, smaller moons, some only a few tens of kilometers across, circling close to the planet and weaving among the rings like tiny ice and rock boats. Miranda turned out to be especially strange. Its surface shows towering cliffs, grooved regions, and patches that look stitched together from mismatched pieces. These features hint that Miranda was once pulled and kneaded by tides, possibly broken and reassembled in the deep past. This was a gentle revelation from the Uranus encounter. Even small, cold moons can be reshaped by gravity. They do not need warmth from a nearby star to change. Tidal flexing, impacts, and internal heat can carve canyons and ridges, far from sunlight, over spans of millions of years. As you feel Earth's steady pull holding you to your bed, you can imagine those little moons also held in place, forever falling around Uranus. They trace the same paths again and again, each orbit a quiet echo of the balance between motion and gravity that keeps them aloft. The Uranus flyby lasted only days, yet it produced more information than centuries of watching from Earth. With no fuel to slow down, Voyager 2 simply continued onward, its path bending under Uranus's gravity and settling into a new course, aimed at the most distant giant, Neptune. From the year 1986 to the year 1989, the spacecraft cruised through the deep space between the ice giants. Sunlight weakened as the distance grew. The pressure of light on its surfaces became almost feather-light, and the sun shrank toward a bright, small star. Radio messages from Earth now took more than 4 hours to arrive, and the answers took just as long to come back. Teams of engineers and scientists sent carefully prepared instructions, then waited. Days passed between planning and outcome, a slow conversation across the dark. In the month of August 1989, Voyager 2 approached Neptune. It swept just a few thousand kilometers above the cloud tops, closer than it had flown near any other giant. Once again, its cameras woke into rapid work, catching the planet's face as it swung slowly past. Neptune's atmosphere turned out to be more restless than Uranus's. Voyager 2 saw dark storm systems, including one called the Great Dark Spot, roughly the size of Earth, and bright, high clouds made of methane ice. In sunlight, they cast tiny shadows on the deeper, darker layers below. By tracking the movement of clouds, scientists measured winds racing at hundreds of meters each second, more than 1,000 kilometers per hour. These are some of the fastest winds seen on any planet, circling a world where sunlight is less than 1% of what reaches Earth. From your room, that might sound fierce, but remember how distant this activity is. These winds rush through a thin, remote atmosphere that no human has ever felt. They are patterns in gas, unfolding calmly on a huge scale, far beyond anything that could touch the quiet air around you. Like Uranus, Neptune carries a tilted, off-center magnetic field. Voyager 2 found its magnetic axis leaning by a little under 50 degrees from the spin axis. Once again, the data pointed to a dynamo not in a tiny metal core, but in a deep, slowly churning shell of conductive fluid. Neptune also has rings, faint and dusty. Some of them include bright arcs, clumps where particles gather as if held in place by invisible hands. Later Hubble observations refined the details and even saw some arcs shift, but Voyager's brief glimpse proved that the rings were truly there. One of the most haunting discoveries came from Triton, Neptune's largest moon. Voyager 2 showed Triton as a pale world with nitrogen ice, strange smooth plains, and dark streaks. Some of those streaks came from geyser plumes, jets of gas and dust rising kilometers above the frozen surface. These plumes are likely triggered when sunlight gently warms dark patches beneath clear ice, causing gas to build up and escape in narrow bursts. Even at that great distance, where the sun is small and cold, small inputs of energy can stir a moon enough to shape its surface over time. From Earth, Triton had been a dot. Up close, it became a landscape with seasons and motion. In the same way, the flybys turned Uranus and Neptune from abstract symbols into real places, each with moons that tell their own quiet stories about ice, gravity, and the slow work of time. After Neptune, there were no more scheduled planets. Voyager 2's remaining fuel was needed for attitude control, not for big course changes. Its path carried it away from the Sun, joining Voyager 1 on a slow journey outward, leaving the realm of planets and heading toward interstellar space. Decades later, both Voyagers still speak. Their power supplies grow weaker each year, but they continue to send back bits of information about charged particles and magnetic fields in the outermost reaches of the Sun's influence, where the solar wind thins and mingles with the gas between stars. It can be soothing to picture those aging machines coasting in darkness, antennas steady, instruments humming. They are small emissaries from your world, moving far beyond the orbit of Neptune, carrying a record of human sounds and images and a quiet proof of how far curiosity can travel. With the Neptune flyby complete, our direct visits to Uranus and Neptune ended. No orbiter has yet circled an ice giant. No probe has yet parachuted down into their deep blue atmospheres. Most of what we know from up close comes from those few intense days when Voyager 2 rushed past. Afterward, our attention returned to telescopes. In 1990, the Hubble Space Telescope lifted above Earth's air. From its orbit, it watched Uranus and Neptune in detail, tracking how clouds brightened and faded from year to year as the planets slowly rotated and advanced in their seasons. Ground-based observatories improved as well. Telescopes on mountaintops in Hawaii, Chile, and other dry, high places used adaptive optics to sharpen their view. In infrared light, they mapped warm and cool bands in the upper atmospheres, revealing patterns the eye alone could not see. These observations showed that Uranus is not always as bland as Voyager's first glimpse suggested. Near its equinoxes, when the sun crosses over its equator, bright storms and bands appear more clearly. Neptune's dark spots, meanwhile, appear, drift across the globe, and then gently fade away. Watching this slow weather is like watching a distant ocean from a cliff. Waves rise and fall, but from far away they seem almost serene. On Uranus and Neptune, winds and clouds respond to sunlight, rotation, and internal heat, playing out over years instead of days. In recent years, the James Webb Space Telescope has added another layer of insight. Observing in infrared wavelengths, it can see the faint glow of heat from high clouds and rings, and it can tease out the spectral fingerprints of gases like methane in far more detail than before. James Webb's images of Uranus show bright, thin rings and delicate structures in the polar regions, while its views of Neptune highlight cool and warm zones in the atmosphere. Each new observation tightens our models, turning the first rough sketches from Voyager into more careful portraits. Through all of this, the planets themselves simply continue. Uranus rolls along its tilted path, completing a single orbit in about 84 Earth years. Neptune, farther out, takes about 165 years to circle the Sun. Their progress is slow enough to outlast many human lives. As you breathe in and out, the span of a breath is tiny compared with even a single Uranian day. Yet your breathing and those orbits are connected by the same physics: inertia, gravity, and the steady passing of time, from heartbeats and seasons to the turning of entire worlds. From Earth we send out radio questions. How fast are the winds? How strong is the magnetism? How bright are the clouds today? Light and radio waves cross the emptiness, and returning data slowly fill in the missing pieces, like careful strokes of paint on a wide, faint canvas. The story that has emerged so far is one of family resemblances and quiet contrasts. Both Uranus and Neptune are rich in water, ammonia, and methane. Both wear rings and host many moons. Both have oddly tilted magnetic fields and deep, cold atmospheres under thin sunlight. Yet Uranus seems to leak very little of its internal heat, while Neptune shines with more warmth than it receives from the Sun. Uranus rolls sideways. Neptune tilts more modestly. Uranus often appears placid, Neptune more stormy. How did two similar worlds grow into such different characters? To answer that, scientists build models of their interiors. They picture a small, dense core of rock and metal wrapped in a thick mantle of hot, compressed water and other ices, all beneath an outer envelope of hydrogen and helium. They calculate how heat and material might slowly move inside. The models must match the measured mass, the slight flattening at the poles, and the magnetic fields that Voyager 2 recorded. They are also guided by temperatures, winds, and atmospheric compositions measured by Hubble, by ground telescopes, and now by James Webb's sensitive instruments. Even so, more than one internal layout can fit the same data. Without an orbiter to map the gravity field in detail, or a probe to descend with instruments through the clouds, the exact layering of those deep mantles remains uncertain. Like a book we have only lightly pressed between our hands. Instead of feeling frustrating, that uncertainty can be quietly pleasing. It means there is still more to learn, still reasons to dream up new missions. The ice giants are not solved puzzles. They are open questions, inviting future explorers from your small blue world to come closer. As you drift, you can let one gentle question linger. Why do some worlds hold on to their heat and storms, while others hide their warmth and wear smoother faces? That question touches Uranus and Neptune, but also giant planets around other stars, far beyond the reach of any Voyager. In the next part of our journey, we will step back and place the ice giants into that larger picture, linking their distant blue mantles to exoplanets in other systems and to the way these outer giants help shape comets, small worlds, and perhaps even the history of life on Earth. Now that our eyes and instruments have traced the clouds and rings of Uranus and Neptune, it is natural to wonder what lies beneath. When you hear the phrase ice giant, you might picture frozen shells. But inside these worlds, the story of ice becomes far stranger and more fluid. If you could drift slowly downward through an ice giant's atmosphere, the blue haze around you would grow darker and heavier. Hydrogen and helium would thicken into deep winds. Methane would fade from view, and the pressure of the overlying gas would rise with every silent kilometer. Far below the clouds, where no sunlight reaches, molecules are pressed so tightly together that water and other ices can no longer behave as familiar solids or liquids. They enter exotic states, part crystal, part fluid, where atoms slide yet still hold a repeating cage-like structure. Laboratory experiments on Earth try to recreate these conditions with powerful lasers and diamond anvils. For a brief moment, researchers can squeeze tiny droplets of water to pressures millions of times greater than the air resting gently on your chest as you breathe in and out tonight. In some of those experiments, water becomes what is called superionic. Its oxygen atoms form a fixed lattice, while charged hydrogen ions move more freely, carrying electric currents. Inside Uranus and Neptune, such layers may act as vast, slow-moving electrical oceans. Those deep, conductive layers help explain the strange magnetic fields that Voyager 2 measured. Instead of one neat bar magnet aligned with the spin, patches of moving, charged material far from the center may create a lopsided, tilted field, turning and wobbling through surrounding space. If you imagine a lantern whose flame is off-center, its light will fall unevenly on the walls of a room. In a similar way, an off-center dynamo spreads magnetic influence in unexpected directions, shaping how charged particles spiral and where invisible curtains of aurora can quietly glow. Deep beneath that, closer to the heart, there is thought to be a compact core rich in rock and metal. It holds only a modest fraction of the planet's radius, but much of its mass. Around it, the vast mantle of water, ammonia, and methane blends gradually with the lighter gases above. These layered worlds are not just curiosities in our own system. When astronomers look outward and find planets around other stars, they see that sizes similar to or a bit smaller than Uranus and Neptune are among the most common. Ice giants and mini-giants seem to be a favored cosmic outcome. Most of those distant planets are detected indirectly. One method watches for tiny dips in a star's light when a planet crosses in front, like a small shadow drifting across a distant lamp. Another senses the gentle tug of a planet's gravity, making the star wobble slightly toward and away from us. From those faint signatures, astronomers can infer a planet's size, its mass, and sometimes even the presence of thick atmospheres. Many worlds they find are neither small rocky spheres like Earth nor immense gas giants like Jupiter, but something in between, rich in volatile materials and deep mantles. In that wider family, Uranus and Neptune become reference points, nearby examples of a class of worlds that seems to fill the galaxy. By understanding the structure and behavior of our own ice giants, we gain a quiet key for reading the properties of countless unseen planets circling other suns. It is almost like learning the climate of two distant, cold oceans and then recognizing similar patterns on weather maps from faraway countries. Once you know how such systems move and breathe, the faint clues in their clouds and winds start to make more sense, even when details remain blurred. Some of those exoplanets orbit very close to their stars, closer than Mercury is to the Sun. Under such intense heating, the outer layers of an ice-rich planet can puff up or even slowly escape, forming hazy envelopes. Their skies may be laced with exotic clouds unlike any we see on our own world. Others circle at cooler distances, where water and other ices can survive deep below. In those cases, the planets may look, in broad outline, more like scaled cousins of Uranus and Neptune. We cannot yet see their rings or moons, but their masses and sizes whisper of familiar internal balances. As you lie here, your body warm and held by Earth's gravity, the thought that ice giant-type worlds are common can be oddly comforting. It suggests that the processes that built our system are not rare tricks but shared habits of nature, repeated quietly around many different stars. The reach of Uranus and Neptune extends inward as well as outward. Their gravity shapes the orbits of countless smaller bodies in the Kuiper Belt, a broad, icy region beyond Neptune, and in even more distant reservoirs of comets that loop through the solar system on elongated, patient paths. In some models of solar system history, the giant planets did not begin exactly where we see them now. They may have migrated slightly, trading energy with swarms of planetesimals. As they moved, they could have scattered comets inward, delivering extra water and organic molecules to the inner worlds. If that picture is close to the truth, then the water in your glass, the moisture in your lungs, and the oceans that cradle life on Earth may owe part of their abundance to quiet gravitational nudges from the ice giants. Long ago, when the young sun was still wrapped in its birth cloud of gas. In this sense, Uranus and Neptune are like distant gardeners, their orbits gently flinging icy seeds toward the warmer ground closer to the sun. Most seeds missed, some were lost, but enough struck and melted to help fill basins, carve rivers, and support the long unfolding of life on your planet. Comets that still wander through the inner system today carry records of that earlier time. Their ices preserve ratios of elements and isotopes that tell us about the temperature and chemistry of the region where they formed. Each one is a frozen note from the workshop that built the ice giants and their kin. When a comet's path brings it near the sun, its ices warm and turn to gas, forming a glowing coma and tail. From far away, this may look dramatic, but most such visits are quiet passages. The nuclei are small and space is vast, so the show is more like a distant campfire than a storm near your door. By analyzing the light from those comas, scientists infer the mix of water, carbon compounds, and other molecules locked in the ice. Some of those same ingredients are woven into your cells and bones. They have traveled from ancient stars, through icy bodies, into oceans, and finally into living tissue. In that long journey, the outer giants act both as barriers and as bridges. They block some incoming objects, capture others as moons, and steer still more into paths that cross the orbits of the inner planets. Their massive presence makes the architecture of the solar system more sculpted than random. If you think of the solar system as a great slow dance, then the ice giants are partners who mostly keep to the outer edge of the floor, yet their steps influence the motion of many smaller dancers. Asteroids, comets, and dwarf planets all respond to the subtle pull of their passing turns. This outer choreography has echoes in other systems. Around many stars, we see hints of belts of debris, gaps in dusty disks, and structures that suggest unseen planets carving paths. Ice giant analogs may be out there, shaping comet clouds and influencing where rocky, life-friendly worlds can form. Back on your own small blue world, astronomers use instruments that spread starlight into spectra to look for signs of atmospheres on some exoplanets. In a few cases, they have seen traces of water vapor and haze, tiny clues that atmospheres on distant giants may be layered and dynamic like those we know. The James Webb Telescope, with its sensitive infrared eyes, is beginning to probe the skies of some of these worlds more deeply. By measuring how starlight filters through a planet's atmosphere during a transit, Webb can pick out the faint signatures of molecules, building a first sketch of alien weather. When scientists compare those exoplanet spectra to the light from Uranus and Neptune, they are looking for family traits. Do the clouds form at similar temperatures? Are methane and other gases present in similar amounts? Do any of these remote giants show hints of deep, hot mantles or strong winds? In this way, the ice giants serve as quiet translators between your backyard sky and the wider galaxy. They turn abstract models into concrete examples, and those examples, in turn, help make sense of planets we can barely see, transforming faint dips of light into richer, more grounded stories. There is another connection as well, more personal and immediate. Many of the atoms in your body were made in ancient stars and in stellar explosions that scattered heavy elements into space. Those atoms later sank into disks of gas and dust around newborn stars, where planets like Uranus and Neptune took shape. Some of that material stayed in icy realms, locked into mantles and cores far from warmth. Some drifted inward and joined the building blocks of Earth. Over vast spans of time, those shared ingredients were heated, mixed, and folded into rocks, oceans, air, and eventually into the cells that now quietly repair themselves as you rest. When you feel your heartbeat, you are sensing a pattern sustained by elements that once flowed in clouds between the stars. The same carbon, oxygen, and nitrogen appear in the atmospheres of giant planets and in your blood and breath, rearranged into different bonds but drawn from a common cosmic pantry. Seen this way, the difference between an ice giant and a living body is not in the basic building blocks but in the arrangement and the energy flows. On Uranus and Neptune, energy moves mostly as heat and winds. In you, it moves as metabolism and thought, yet all follow the same physical laws. That recognition is the third, gentlest wave of intrigue in this story. When we study distant planets, we are also studying the context of our own existence. We are asking how common certain planetary recipes might be, and where conditions that allow liquid water and complex chemistry might quietly arise. Ice giants show that nature likes to store water and other volatiles in large, cold reservoirs. They remind us that not all habitable environments need to sit on the surface of a sunlit world. Oceans might exist beneath ice shells on moons, or deep under the clouds of distant planets warmed from within. For now, our technology is far from dipping a probe into those hidden seas, but the idea itself changes how we think about life in the universe. Instead of looking only for second Earths, we also consider layered worlds, moon systems, and underground oceans as potential hosts for slow, patient forms of biology. As you lie in the dark, wrapped in the thin, breathable layer of Earth's atmosphere, you can imagine other beings, if they exist, wrapped in very different envelopes of gas and ice. Their skies would be dimmer, their stars smaller in the sky, yet they would share the same quiet starlight that falls on your window. The science of Uranus and Neptune does not answer whether such life exists, but it refines the map of where it might be possible. It extends the zone of interest outward, from warm surfaces like ours to places where heat comes from planet interiors and chemical gradients, rather than from direct sunshine. All of these threads meet back at your resting place. Light from distant exoplanets is captured by mirrors and detectors built by human hands. Data travel along fiber optic cables, arrive in labs and homes, and eventually reach you as images, stories, and quiet explanations whispered over the hum of night. In that sense, every spectrum of an ice giant, every plot of wind speed, every map of a faint ring system is also a reflection of human curiosity. It shows that minds made of star-born matter can look outward, build tools, and then use the results to ask deeper, more patient questions about their own place. Our journey with Uranus and Neptune has carried us from the discovery of distant blue points, through flybys and telescopic watching, into invisible interiors and outward to a galaxy populated with related worlds. The next step is to ask how we might visit them again, not in passing but to stay and watch for many years. In the next part of this story, we will turn to those future plans, to proposed missions that would orbit an ice giant, drop probes into its atmosphere, and linger among its moons, and we will return gently to what all of this means for your small blue world turning quietly beneath your blankets. By now, our journey with Uranus and Neptune has stretched from faint points on old star charts to deep, imagined layers of superheated ice and wandering magnetic fields. A natural question drifts in next, as soft as your own breath in the dark. What happens from here, and who will visit them again? At this moment, almost everything we know from up close comes from a single traveler, Voyager 2, and from careful watching with telescopes that never reach their clouds. It is as if we flew past a distant coastline once, took a few photographs, and have since studied only the waves from far offshore. Planetary scientists dream of changing that. For years, they have sketched quiet blue spacecraft that would not just pass by an ice giant, but settle into orbit, looping again and again, listening to its gravity and magnetism, and sending a small probe down into the high, cold air. In those designs, a Uranus orbiter carries an atmospheric probe shaped like a rounded cone. After a long cruise through deep space, the main craft would release the probe, which would slip into the upper atmosphere and fall gently downward beneath a heat shield and then a parachute. As it descended, that probe would measure temperature, pressure, wind, and composition directly, sampling air that has never touched sunlight the way air near your window does. Each reading would travel upward as a radio signal, then outward to the orbiter, and onward across the silent gulf toward Earth. High above, the orbiter would trace long, slow paths around Uranus, its instruments tuned to tiny changes in speed and direction. Those changes, mapped over many months, would reveal how mass is arranged inside, and help distinguish between different models of the deep, icy mantle and compact core. Other instruments would listen to the magnetic field, watching how the tilted, off-center dynamo sweeps through space and how charged particles flow along it. Over time, a living picture would emerge, showing how that strange field breathes and shifts as the planet rotates and orbits the distant sun. Cameras and spectrometers would watch the clouds, rings, and moons. They would track storms appearing and fading, map ring particles, and study subtle colors in moon surfaces that hint at ice, rock, or complex organics. The hazy sketch we hold now would sharpen into something more like a portrait. A similar mission to Neptune, perhaps arriving later, would carry its own dreams. There, an orbiter could keep watch over restless storms and over Triton, that captured moon with possible hidden layers and gentle geysers. Every pass would test ideas about oceans and heat far from any direct, warm sunlight. To reach either world, a spacecraft must accept a different pace than life on the surface of your small blue planet. Journeys are measured in many years. Engineers and navigators work through launch, cruise, arrival, and long orbital mapping, knowing that some of the final data may reach the next generation. When mission planners trace those timelines, they fold in gravity assists, radioisotope power, and slow changes to orbits. They must think in spans that stretch beyond a school career or a single job. It is a kind of patience that matches, in a small human way, the unhurried motion of the planets themselves. You might picture a scientist at a desk late at night, a mug of cool tea beside them, refining a design for an ice giant probe while the rest of the house sleeps. Somewhere else, a student runs simulations of atmospheric flows, imagining data that a future orbiter might send back one quiet day. All of that work happens on the same small blue world where you are resting. The same gravity holding you to your mattress holds the ocean of air above your head and keeps the laboratories grounded while they send digital whispers outward, preparing for journeys their designers may never personally see completed. In parallel with mission plans, telescopes continue their steady watching. Hubble, ground-based observatories, and the James Webb Telescope each add a little more detail to the story every year, like careful stitches in a vast quilt, brightening some patches and revealing subtle textures in others. New images show how storms change with seasons, how rings respond to small moons, how auroras flicker where magnetic fields guide particles into the thin upper air. Spectra refine our sense of what gases float above, and how heat moves from the secretive interiors outward toward the blue, glowing tops of the clouds. In the background, the discovery of exoplanets continues as well. With each new world found, the context for Uranus and Neptune grows richer. These two distant giants are no longer oddities on the edge of a single system, but guideposts in a much larger landscape of planets scattered throughout the galaxy. When scientists talk about habitability now, they do not speak only of Earth-like worlds with lands and seas. They also ask about icy moons, underground oceans, and chemical gradients inside thick mantles. The lessons drawn from ice giants flow into those questions, widening the kinds of places where life might quietly arise. Even if no living chemistry ever stirs beneath Uranian or Neptunian clouds, the knowledge we gain from them can help us recognize the signs of life elsewhere. By understanding what a lifeless giant looks like in detail, we can more easily spot the subtle fingerprints that might signal biology on smaller, warmer worlds. For you, listening in the dark, these long-term projects might seem far away in both distance and time. Yet they loop back into everyday life in small ways. Technologies made for deep space often find uses on Earth, and the shared effort of such missions quietly threads together people across many countries. Engineers who design navigation software, craftspeople who polish telescope mirrors, and students who learn to decode spectra all become part of the same unfolding story that includes Uranus, Neptune, and your own evening routine. You, they, and the ice giants all share the same starlight and the same physical laws. As we near the end of this quiet journey, it can be soothing to trace our path once more. We began on a calm night under Earth's sky, where distant planets moved unnoticed behind city lights and thin clouds, while your heartbeat and breath marked time on a scale of moments instead of millions of years. We visited the past, when Uranus and Neptune were first suspected and then confirmed, worlds added to the solar system through careful watching and careful mathematics. We followed Voyager 2 as it slipped through their neighborhoods, turning pale dots into places with rings, storms, and families of moons. We imagined the strange interiors where water becomes something more than liquid or ice, where superionic layers may carry electric currents and feed tilted magnetic fields. We stepped outward to exoplanets, seeing how ice giant-like worlds appear again and again around other suns as a common planetary shape. We traced how the gravity of these distant giants shapes the orbits of comets, and how some of those icy messengers may have helped deliver water and organic molecules to the inner worlds, seeding the conditions that, over long ages, allowed oceans and life to develop on your small blue planet. And we looked ahead, to planned and imagined missions that might one day orbit an ice giant, drop probes into its air, and linger long enough to watch whole seasons of weather unfold. Those future explorers, robotic and patient, will deepen the bond between your world and those far, faint blue companions. Through all of this, one thread has stayed close. The same quiet light that reflects from Uranus and Neptune, travels across space, and lands on telescope mirrors also falls softly on your window, your hands, and the blanket that covers you now. You live inside that same luminous, shared universe. The elements in your bones and blood were forged in earlier generations of stars, the cosmic elders whose ashes became the raw material for planets and for you. The ice giants hold some of that heritage in deep, cold layers, while you carry another portion in warm, constantly renewing tissue. As you notice the gentle weight of your body on the mattress, you are feeling gravity, the same simple pull that keeps moons circling Uranus and Neptune and keeps those planets bound to their wide orbits. The law that holds whole worlds in place is the same law that holds you safely to your bed. Outside, Earth continues to turn. Somewhere above the horizon, unseen through roofs and clouds, your planet is rotating eastward, carrying you with it. Far beyond that, Uranus and Neptune move almost imperceptibly along their paths, completing orbits that span longer than a human lifetime. All of these motions are slow, steady, and indifferent to hurry. They set a background rhythm against which your own days and nights unfold. Knowing this, you can let some of the urgency of daily concerns loosen, at least for now, while you rest in the middle of these vast, reliable cycles. If your mind is still lightly awake, you can choose a single image to keep you company as sleep approaches. Perhaps it is the pale ring of Uranus tilted on its side, or the deep blue of Neptune with a single dark storm turning slowly, both worlds lit by a small, distant Sunday. You might picture quiet light leaving that sun, crossing empty space for hours upon hours, brushing past the ice giants and continuing outward, some of it eventually reaching Earth and slipping through your window to touch the air above your pillow with a softness that is easy to overlook. Down here, your role is simple. Breathe in and breathe out. Let your shoulders and jaw unclench. Let your thoughts drift the way a spacecraft drifts between planets, coasting on a path that no longer needs effort, held gently by gravity and guided by the quiet momentum of what has already been set in motion. The ice giants will keep turning whether you are awake or asleep. Their clouds will rise and fall. Their magnetic fields will sweep and twist, and future explorers will continue to plan visits. None of that requires your attention tonight. Your part in the story for now is simply to rest. If you ever wish to drift through this journey again, from your small blue world to the distant, tilted giants and back, it will be waiting for you, unchanged, like the patient orbits of Uranus and Neptune themselves. For this night, you can let the story fade and allow sleep to rise up gently to meet you.